Hi, my name is Rebecca and my partner's name is Mike, and today we'll be discussing the design of load frequency control using fuzzy logic for single area power networks. So in today's presentation, we're going to go through a brief overview of power systems and what is load frequency control, and then dive into the fuzzy logic and how we use this method to achieve our results. So first off, a single area power network, which we can also call a single phase power network, it's a self-contained system that can operate with one or more generators that supply power to different loads. And then these generators work to maintain a frequency of usually around 60 hertz. But however, there's fluctuations that can occur due to changes in supply and demand, and if demand increases, the frequency can rise, and if supply surpasses demand, the frequency can decrease. And so these fluctuations can impact the stability of the system and lead to blackouts as well. So LFC, load frequency control, is a method that automatically adjusts the generator output to respond to these variations in order to maintain balance. And traditionally, PID controllers are what we have used for LFC, but they do have limitations because they have fixed parameters, and their response to they struggle with nonlinear system behavior. However, FLC, fuzzy logic control, is a good alternative because it can mimic human reasoning to make decisions that are based on uncertain inputs. So unlike the PID controllers, FLC doesn't require an explicit mathematical model. It's more adaptable to grid fluctuations. And so this project will focus on implementing a single input fuzzy logic controller. So we used a single input FLC in MATLAB Simulink for single area power network. And our system model here, there is a turbine, governor, synchronous generator, and a rotating load that we have modeled in order to implement the feedback control loop. And as we see here, so the transfer functions for each component were derived from previous studies, and we chose the following parameters for the inertia constant, damping coefficients, and then the governor time and turbine time constants in order to model it in this way. And where it says controllers, where we replaced that part with the controller that we're trying to simulate. Now a bit more into fuzzy interference. So fuzzy interference is the process where we map the inputs to the outputs using fuzzy logic. So traditional FLC systems, there are two inputs, the frequency error, defined as delta F, so the reference frequency minus the actual frequency, as well as the rate of change of frequency error. But the single input part of it is what simplifies this by converting these two inputs into a single input using a method called the sign distance method. And so our final result of the single input that we need is U equals to the scaling factor, which is Ks, and then alpha is also the weighing parameter. So then we can use this single input and feed it into the fuzzy interference system, which will determine the necessary power we need to change or to restore the frequency balance. And this, as a single equation, can easily be implemented with Simulink blocks such as gain and multiplication, addition, so on, derivative. So a bit more of the fuzzy interference system. There's a rule base here. So it applies the set of rules here that we see to determine the output power adjustment, which will be delta P. And then these rules are shown here using these linguistic variables. There's NB, which means negative big, so we significantly would decrease the power, or NM, we'd moderately decrease the power. And then if it's 0, no change. And then also in the reverse, so if it's positive, medium, we'd moderately increase the power. So then each of the input is assigned a a membership function, which is represented by a triangular function. So then the corresponding output membership functions will determine like the necessary power adjustment. To better visualize this here, we can take a closer look at what these membership functions are. So when we use these, they kind of define how the controller will interpret the input signal and determine the appropriate output adjustment. So if we start here with the input membership functions, we can categorize the input variable u, which was previously defined using the sign distance method, into 7 different linguistic terms. So as we just said, NB, NM, NS, and so on. And then each of these can be represented with a triangular membership function, which is trimf in MATLAB. And it defines like the degree to which this belongs to a value that is given within a certain range. So then the values inside the brackets can represent the lower, middle, and upper bounds for each term. So here, for example, in the input table, we have like NB, which is defined as trimf, u, the input, and then -1, -1, -0.7, meaning that any value that is below -0.7 is strongly classified as negative big with full membership at -1. And then 0 would mean like values close to 0 as defined there, and 0 would have the strongest membership in this category. And similarly with the output variable, which is delta P, it represents like the required power adjustment, and we use the same 7 categories. And then these functions are also triangular and follow the same structure as the input. So then by mapping these input and output functions together, the fuzzy control will determine how much power correction is needed based on the frequency deviation. So it plays a crucial role in ensuring smooth, accurate frequency restoration within the power network. So then here they can be visualized using MATLAB, and we can see how these membership functions allow the fuzzy interference logic to determine the necessary control actions based on the degree of membership to a certain category. So it's much more complex than just the regular PID controller. As you can see there, it can be much more accurate, as we'll see. And now I'm going to pass it to my partner, Mike, who's going to go through the implementation of this into MATLAB and Simulink and the results that we acquired.
Using the fuzzy logic designer in MATLAB, we incorporated our membership functions and rules to the fuzzy logic controller block in Simulink and ran the simulation to observe the results. Obviously, these are the rules you see right now on the screen, which was successfully implemented and snipped from the fuzzy logic block from the Simulink. On to results. Here's our model. We implemented our model in MATLAB Simulink. The process included creating a single area power system model, implementing the fuzzy interference system with defined membership functions, using gain blocks to compute the signed distance input, u. You can see it on the block here. Now running simulation to evaluate the performance. Here we see our Simulink scope output displaying the frequency deviation over time. Here we compared PID and fuzzy, where in theory fuzzy was supposed to outperform the PID controller. These scope outputs represent how the system responds to disturbances and how the frequency deviates from its normal value. As we can see, PID tends back to zero frequency deviation, which is ideal, where fuzzy is supposed to just outperform PID and still tend to zero. Unfortunately, here we measure a steady state error of 10 millihertz. We think it's most likely due to the tuning issue, where our fuzzy controller produces an offset. Next, on to the power adjustment applied to the controller. This graph shows how the control system modulates power to compensate for frequency deviations. When deviation is large, then we observe significant power reaction. which then gradually reduces as the system stabilizes. As you can see, PID and fuzzy controllers operate similarly, where fuzzy is supposed to outperform. However, as even though the responses look similar, the fuzzy controller does induce a steady state error again, which there's also which you're gonna see later. Here the comparison. So we measured overshoot, rise time, and settling time. Here you can see that overshoot in the fuzzy logic controller is lower. However, the rise time is longer, and settling time is pretty much the same for both. Obviously, these are not ideal results for the fuzzy logic controller since it can operate a lot better than PID can. To conclude, this project has shown us that using a single input FLC can effectively stabilize frequency fluctuations in a single area power network if designed correctly and outperform other controllers like PID. Unfortunately, we weren't able to achieve those results, but we came really close. Performing this project, we learned that single input FLC handles nonlinearity well. It reduces computational complexity, improves response time, and adaptability. Future work could involve extending this approach to multi-area power systems and incorporating artificial intelligence techniques for further optimization. Thank you.